Um, okay, no class next week. March 1st is Samil절. So we're not going to have a class. We're going to meet on March 1st. And on March 3rd, I have a trip. So I have to cancel, the class. So for makeup, I'm thinking of March 11th, which is Friday. Two of you might not work for this. So alternatively, if I can find, classroom we can do on Thursday as well, since you are coming on Thursday. So we have a class at 9. Regular schedule is 9, right? So if possible, we can meet, one more time on Thursday afternoon. I don't know what you want to do. I don't know why, so many are absent today. So, but we can decide, this, next week, okay, when we have more, not next week, when I come back from a trip, which is 9th, which is Tuesday, we can, no, 8th. We can decide, on 8th when we meet. Either we can meet on Tuesday afternoon, somewhere here, either seminar room or depending on, what is available. Or we can meet on 11th, on Friday. Okay. Sorry for this cancellation, but as I said at the beginning, I have a few trips planned this semester. So I think I have to cancel about 3 lectures that I reschedule either on Thursday or Friday, depending on, what you want. So think about it, and then we'll discuss, when I come back from a trip. Okay? And in the meantime, I handed out first homework. Due is March 8th, so Tuesday. So next time when we meet, there's no class next week, so it's a good time for you to do some homework. And the first problem is a straightforward problem. And in class, I just derived the result shown in figure equation 1, but I just want you to go through by yourself to get equation 1. So that is just straightforward, Taylor expansion. Then you will can get the answer. And the problem 2, I just want you to make sure that you understand, the material derivative. So first thing that I ask you to do is to find the path line of a fluid particle located at a location, at a point. Then I'll ask you to find x of t and y of t. Remember that dx dt is u, dy dt is v, right? So you can solve, the ordinary differential equation easily. And then by taking second time derivative of x of t and y of t, you will get an acceleration. So that's one way to get the acceleration of a fluid particle. The other way to get the acceleration is use material derivative, as we discussed. So, so compare those two. They should match, right? In class, we solved the Navier-Stokes equation for inclined plane, and this time I changed the problem a little bit so that you're looking at a flow outside of a circular cylinder. So water is flowing down on the surface of circular cylinder, and so you can solve this problem exactly, and the Navier-Stokes equations in the cylindrical coordinates are necessary to solve this problem. So if you look at the next page, you can find the Navier-Stokes equation in the cylindrical coordinates. The next problem is just dimensional analysis that we discussed, so it should be easy. And the last one is equation of vorticity that we started to talk about last week, or on Tuesday actually. Okay. Okay, so due is Tuesday, and the one thing that I want to point out is, I encourage you to discuss, okay, the homework, so you can discuss, what the problem is, how to solve, and that kind of thing. Okay, so you are absolutely, welcome, to discuss with anyone. I mean, in the class. But when you write a homework, you have to do your own. Okay. Last semester I noticed that some people don't do their homework and they just copied it. Okay. And this time I'm not going to accept any homework that I think is a copy. Okay. If you want to copy someone's homework, it's better not to do it. And at least you'll get a 0 instead of minus, okay? So you don't have to waste your time to copy someone else's homework, without learning anything. Homework is for learning. Okay? If you don't do by yourself, you're not gonna get anything. So why wasting your time to copy someone's homework? And also, it's obvious, whether a homework has been copied or not, right? Anybody can tell. So if I see something like that, then I'll give you some points which are negative. Okay, so don't do that. Okay, so, but whenever you have question, discuss with someone. Okay, and also you can come to me, and I'm happy to discuss anything in the homework if you want to. Clear? Okay. So just for some of you who came late, no class next week. March 3rd class is canceled, and we'll decide, when we meet for makeup class when I come back on March 8th. Okay. So we'll discuss that. One possibility is, the Thursday afternoon or Friday. So think about it and let me know. Let me review briefly what we did on Tuesday. And we talked about dimensional analysis and non-dimensionalization. And then we noticed that we'll get a Reynolds number and Froude number and all other physical dimensionless parameters by dimensional analysis or through Poquin's pi theorem or non-dimensionalization. So important parameters in here is Reynolds number, which is defined by rho u L divided by mu. Okay. So rho is density, u is speed of body, L is dimension, the length of a body, and mu is dynamic viscosity. Of course, this is a dimensionless, okay, so it doesn't have any dimension. Then through non-dimensionalization of Navier-Stokes equations, we realized that this is nothing but the ratio between inertia force divided by viscous force. Okay. So if viscous force is dominant, then Reynolds number is small. If inertial force is dominant, then Reynolds number has to be large. Okay. So viscosity is a measure of resistance, basically, right? So viscosity is trying to stop the flow, and on the other hand, the inertia is trying to move, the fluid particle, make fluid particles move, and therefore, if flow is slow, then obviously viscosity is important. On the other hand, if fluid particle moves with a very fast speed, then the inertia is large. Therefore, Reynolds number is large. That's what this guy is. Okay. Another interpretation of Reynolds number is the following, using the time scale argument. Here we use the argument based on forces, and the other way to interpret another way to interpret Reynolds number is to use the argument based on time scales. So here I can rewrite this in the following way. So I divide by rho in this way. So I divide by rho, divided in the numerator and denominator by rho. And then I divide by L squared. So I have a U divided by L and 1 over L squared. So this is exactly the same as this. I just divided by rho, the numerator and denominator by rho, and then L squared. I had the L here, so when I divide by L squared, I have only L here. So what is this? Numerator, U divided by L. So this is a dimension of what? It's the length divided by time divided by the L. So the dimension is 1 over time. So I can say this is my time, characteristic time for inertia. Okay. So T inertia is nothing but L divided by U, meaning that if you have the body whose length is L, then L divided by U is the time to take a fluid particle moves from front of the body to the rear back of the body, right? So that's why I said this is a T inertia. On the other hand, this is kinematic viscosity nu, and this has a dimension of L squared divided by T. So when I divide it by L squared, which is a dimension of 1 over capital L squared, and then I end up with 1 over T dimension. Since that time is associated with the viscosity, so I said this is a time scale of viscosity. Okay. So at the end, the Reynolds number measures T viscosity divided by T inertia. This is associated with time. This is a time associated with the movement of fluid particles, so that's why we call T inertia. On the other hand, this T viscosity is a time scale associated with the kinematic viscosity, okay, or dynamic viscosity, it doesn't matter. But anyway, so this is a measure of Reynolds number. So what is if Reynolds number is large, then in terms of time scales, we know T viscosity or T inertia is much smaller than T viscosity. On the other hand, if Reynolds number is small, T inertia is much greater than T viscosity. So for Reynolds number to be large, this guy has to be smaller than this. For Reynolds number to be small, this guy has to be smaller than the denominator. So what does that mean? Time scale associated with the Reynolds number is time scale associated with the inertia for high Reynolds number is very, very small. Okay. So you will see more highly fluctuating flows for large Reynolds number. Small time scale means the period is small, meaning the frequency is large. So something is moving very fast. Okay. It is oscillating, with a small period. So typically what you see is if you measure a velocity at a given location, let's say point 0, for Reynolds number, if Reynolds number is a moderate or small, then you can see oscillation like this. So this is a Reynolds number 1. And on the other hand, if you measure a velocity at a given point 0, then you might see something like this. If Reynolds number 2 is greater than Reynolds number 1. Because the inertia, the time scale associated with the inertia is much smaller, so it's highly fluctuating. Okay, so as we'll discuss later, when Reynolds number is large, you see something like this, and then we call this turbulent flow. And rather, if you have a velocity field which is smooth, then we call this as a laminar flow. So, for example, this is a typical T inertia for this Reynolds number, but in this case, the oscillation occurs on this time. So this is T inertia for high Reynolds number. So the time associated with the inertial force or inertia is much shorter when you have a high Reynolds number flow. And then this guy is small, and then Reynolds number becomes large. Does it make sense? No? So the point is, when you have a large Reynolds number flows, you might see, highly fluctuating, the velocity field, because the time scale associated with the inertia is smaller. Okay, and we'll discuss the turbulent flows a little bit later for high Reynolds number flows. But one of the points that I want to make is Reynolds number can be understood as a ratio between two different forces. One is the inertial force and the other is viscous force. And also you can understand, Reynolds number as the ratio of two time scales, one associated with inertia and one associated with the viscosity. And as Reynolds number increases, the characteristic time scale for inertia gets smaller and smaller, and therefore you might see, highly fluctuating velocity in the flow. Okay. Okay, that's one thing that we discussed, and the other thing that we started to discuss was vorticity. So vorticity is defined as a curl of velocity in this way, and there are three components. It's a vector, and for example, for two-dimensional flow, omega x and omega y are 0, and omega z is defined by dv dx minus du dy. Right? In three-dimensional flows, you have three components. And last time, I took an example for two-dimensional flow, and then I showed you what this term represents. And so dv dx is a difference of vertical velocity in two different x locations. So if this velocity is bigger than this velocity, then the whole line has to rotate like this, right? And likewise, this line can rotate if u decreases in y with a negative sign. Okay, and that's what. So if this is positive, then you see the whole rotation. When I say positive, the line is rotating in the counterclockwise direction. And so this is a mean rotation rate of fluid elements. So if you call this is A, B, and C, and this is the rotation rate or angular speed, which is dB dx basically, and this is theta dot of AC. This is AB, is given by minus du dy, and then you take the sum, and to get the vorticity. So if this element, this line is moving counterclockwise, if this line is moving clockwise, then when I add up, the vorticity is 0. So even though each line is rotating, the sum is 0. Okay. And the reason why this theta dot AB is dV dx, it can be easily seen because the vertical velocity at point A and is x, y, and so 2D depends on only x and y and t. And the velocity point B is x plus delta x, y and z, right? Y and t, right? And then this guy is v. I can. So let me draw. So at point A, this is the velocity, vertical velocity. At point B, this is vertical velocity, and then I can use Taylor expansion to write this as x, y, and t. And then I have delta x, dv dx, and so on. So this term, dot, 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 means, this is a term proportional delta x squared, which is small because my delta x is so small. And then the difference between this guy and this guy is really this. Okay. And so that's the speed. And to find the angular velocity, what you need to do is delta x dv dx is the difference in the vertical velocity. That has to be the same as delta x. This is arm times angular velocity, which is theta ab dot. Okay, that's why I get theta ab dot is equal to dv dx. Here, this dot means time derivative. So to find the speed, you have to multiply angular speed times arm, which is delta x. So this distance is delta x. You also can see why the theta AC time derivative of angle theta AC is minus du dy, just simply by using Taylor expansion. As an example, we use u is y and minus y, v is x last time to show the omega z is 2, right? That's what we did. And but fluid part, the element doesn't have to rotate as a whole. You can have the rotational flow like this. Another example is u is y and v is 0. Okay. So this time, what happens? I have a fluid element, rectangular fluid element. There is no vertical velocity, so this guy cannot rotate in this way. The velocity here and velocity here, I have only horizontal component. There's no vertical component because v is 0. This velocity and this velocity are the same because they are in the same y coordinate, right? So in this direction, they just move. On the other hand, if you look at the vertical velocity, horizontal velocity at the different y locations, as y increases, u increases. So this guy is moving faster than this. So at the end, what happens? It looks like that. Because this fluid particle is moving faster than this. So at the end, what you get is something like this. So this rotation is 0, but this rotation is not. And therefore, the vorticity, omega z, defined by dv dx minus du dy, is minus 1. Because this guy is 0, and this is minus du dy gives minus 1. The reason, why we have a negative vorticity is this guy is rotating in clockwise direction. But if you look at the velocity field, velocity field looks like this. So this is u as a function of y. So it's linearly increases in y. Okay, so this is the velocity field, and then the vorticity is -1. So if omega vorticity factor is 0 everywhere, then the flow is irrotational. Otherwise, the flow is rotational. So for a flow to be rotational, vorticity has to be 0 everywhere. Also, all three components. So this is my fluid domain. If I have vorticity here, which is not equal to 0, and vorticity is equal to 0, for example, then this flow is rotational. Okay. So that's the definition of irrotationality. And later, we are going to use irrotationality to solve problems. So understanding, what we mean by irrotational is important. So here I mathematically defined vorticity as a curl of velocity. That's the first thing that we did. And second thing what we did is, I gave, the physical interpretation of vorticity, which measures, mean or sum the rotation rates, right? Now, next question is, how vorticity is generated in the flow? Okay, so that's what I'm going to talk about. So we know what the vorticity is, and what I'm going to explain is how vorticity is generated in the flow. So this is a general statement. Vorticity is, in general, generated. Vorticity is, in general, generated at a boundary. When the fluid motion starts from rest. So at t equal to 0, the fluid is at rest. So since fluid is not moving, velocity is 0. And therefore, vorticity, when I take a curl, velocity is 0. So curl of velocity is 0 as well. So I have a 0 vorticity initially. Then I can the vorticity can be generated at a boundary. So in other words, imagine a body like this. So this body, solid body, is at rest at t equal to 0. Fluid is at rest as well. And all of a sudden, this guy starts to move. Okay? Or when fluid, the body is still stationary, flow starts at t equal to 0. Okay. And then the vorticity can be generated at the boundary of this body, okay, this object. The reason is, when you turn on flow at t equal to 0 with the velocity u, and sooner or later you'll see velocity u here, okay, away from body. And then we know the velocity at the boundary has to be 0. It's a no-slip boundary condition because this object is stationary. It's not moving. So fluid velocity has to be the same as velocity of this object. That's a no-slip boundary condition. So here u is equal to 0 from boundary condition. So velocity has to increase from 0 to some value u. And therefore, you have some distribution of u like this. Right? So velocity at the boundary has to be 0, and then velocity far away from the boundary has to be, some constant value, which is the same as this velocity. And then velocity, horizontal velocity increases from 0 to some finite value u. Then if you look at the vorticity in this component, vorticity component, which is perpendicular to this whiteboard, is given by dv dx and minus du dy. If this curvature is very small, then this is negligible. So it's almost vorticity will be determined by du dy. Okay, so this is why. So if you have a flat plate, then you expect almost a horizontal flow. If you have a boundary like this, then of course the flow has to go around. So you have both horizontal velocity and vertical velocity. Okay, because if this component has a horizontal component and vertical component. But if you have a almost a flat plate, or the object whose radius of curvature is very, very large, then it's almost horizontal, right? That's why I can neglect this. If body is is a streamlined body, for example. But anyway, du dy is no longer constant, and so this is not equal to 0. Okay. So even though you start from 0 state, sooner or later you'll see vorticity generate near the boundary. Okay. So that's why I said the vorticity is in general generated at a boundary. Not only the vorticity can be generated at the solid boundary, but also can be generated at the free boundary as well, like a free surface. So this is this is a generation mechanism of vorticity. So obviously I use the no-slip boundary condition, which is really true for viscous fluid. So if I have flat plate, if I have flow like this, for viscous flow, my u at y equal to 0, this is at has to be 0 for viscous flow, right? No slip boundary condition. So this guy increases from 0 to some constant value like this. So the vorticity is generated. But in viscid flow, for which mu is identically 0, then what happens? I have a velocity u here. So this is boundary. Boundary condition at the boundary for inviscid flow is simply the water cannot, or fluid cannot go into the, the solid boundary. So meaning that the vertical velocity has to be 0. But there is no condition for u. So u can be anything that you have, and that's what happens. So in this case, du dy is identically 0 because u doesn't depend on y. So this time, the boundary condition, for u, there's no boundary condition for horizontal velocity, and therefore, vorticity cannot be generated for inviscid flow. So in this case, no vorticity. So what it says here is whenever you have a viscosity, you expect, the vorticity is generated near the boundary. So if you have a body like this, and if you have viscosity, then velocity changes, from 0 to some value. If you have flow like this, okay, and here, and then beyond, this thin region, the velocity is almost constant. Okay, so this is a boundary layer. Where velocity changes, from 0 to some constant value. Okay, so you can expect vorticity inside of boundary layer is non-zero, but beyond that, vorticity is almost 0. So if you look at inside of boundary layer, so this is boundary layer. So inside of boundary layer, omega is not equal to 0. And outside boundary layer, we expect omega is almost 0. Okay. The thickness of boundary layer depends on Reynolds number. So we know there is some layer in which vorticity is not equal to 0, and due to the viscosity. But we were wondering, how big this thickness is. Okay, and that thickness depends on Reynolds number, as I said. How do we know? We can do the scaling argument as we did before. So Reynolds number. So this is inside the boundary layer. Inside the boundary layer. What we know is inertia force is as important as viscous force, or viscous force is as important as inertia force. Because if there is no viscosity, I wouldn't have a zero no-slip boundary condition, right? And then I wouldn't have the vorticity. This time, since I have viscosity, I have a zero velocity, which is a no-slip boundary condition. And therefore, inside of boundary layer, viscosity plays a role. Okay? So, inside of boundary layer, this guy is as important as this guy. But only this layer. So, inertia force is, as we saw before, is U square divided by L, because we have something like inertia force term has a U dot grad U. So this is U squared divided by L. That's how we measure, this inertia force, or when you do the non-dimensionalization, times, the density rho. Viscous force, we typically measure the order of magnitude of this guy divided by U divided by L squared. That's what we did before. And this time, inside of boundary layer, the characteristic length of viscous force is, instead of L, that has to be thickness of boundary layer delta squared. Okay? So previously we have a rho U squared over L, mu times U divided by L squared. That's what we did. And then we end up with the Reynolds number, which is rho U L divided by mu. That's how we get the Reynolds number. Okay? So this was the measure of viscous force. But this time, we are only interested in inside of boundary layer. Therefore, instead of L, that is the length of this body, we are interested in this length scale. And then, instead of divided by L squared, we divide by delta squared to measure viscous force, because we have mu d square U dy squared kind of term. So this term is much bigger than this guy, because delta is smaller than L. So this guy is bigger than mu U L squared for sure, because the delta is smaller than L. And so this is a scaling for viscous force inside of boundary layer. Then I end up with rho U, this is U, rho U L divided by mu times delta square L squared. So this is nothing but what I did. So delta squared goes to numerator, and I have a L in the denominator, and then I put L here, L squared here, so I end up with L in the denominator. So this is just rewriting. Now, this guy has to be order 1, meaning that the order of magnitude of this term has to be order 1, because inside a boundary layer, the inertia force, viscous force is as important as inertia force. So inside boundary layer, inertia force is almost the same as viscous force. Otherwise, I wouldn't get a loosely bounded condition, and therefore this is almost the same to order 1. So L over delta has to be order of what? Mu rho UL. Okay? So I divide by both sides by this. This is nothing but order 1/2 here. So this is nothing but 1 over Reynolds number, and therefore I have Reynolds number like that. This is order of magnitude. When I say this way, the magnitude of this guy is the same as magnitude of this guy. That's what I'm saying. If this is 10, this is about 10, 11, 12, that kind of thing. Okay? So the size of this is almost the same as this. That's what I mean by this. So eventually what we got is, the thickness of boundary layer, delta. So delta is so here delta is the thickness of boundary layer. Thickness of boundary layer, when we non-dimensionalize with respect to body length, is proportional to 1 over Reynolds number, square root of Reynolds number. So what it says, as Reynolds number increases, this guy decreases. So when the Reynolds number increases, the thickness gets smaller and smaller. Okay? So if your Reynolds number is very small, then this number is very large, then basically there is no boundary layer. Actually, everywhere is a boundary layer. Okay? But if Reynolds number is large, then this number is very small. So for example, if Reynolds number is 10 to the 8th, which is a very reasonable number for our application, and then delta over L is what? 10 to the minus 4. So suppose you have a 100 meter ship, then what is the thickness of boundary layer? Delta over L is 10 to the 4th. So if my L is 100 meters, then my delta would be which is centimeter. Okay? So boundary layer thickness is really small. So away from boundary layer, you may think the flow is inviscid and rotational because the vorticity is not generated. So for high Reynolds number flow, the flow can be considered irrotational domain away from a boundary. So in other words, if this is the object, there is a boundary layer near the body, and here omega is equal to 0, and here omega is not equal to 0. So if you look at flow here, then you can think the flow is rotational. Okay? But here the flow is rotational. Even though the thickness of boundary layer is small, you cannot completely neglect viscosity, the boundary layer, because friction plays a role here. Viscosity plays a role here, and that's why you get a frictional drag. Okay. If we completely neglect boundary layer, then there is no frictional drag because no resistance, okay, due to the viscosity. Even though the boundary layer is thin, there is a the viscosity plays a role inside of boundary layer. Therefore, we have a frictional drag. Okay. So the point is, whenever we are interested in the viscous effect, then we have to include boundary layer. But for some reason, if you're not interested in the boundary layer near the boundary, then you neglect that, and then you assume flow is irrotational. Okay. That is only true for high Reynolds number flow. For Reynolds number flow, low Reynolds number flow, the boundary layer thickness is so large, and then vorticity is everywhere, is non-zero everywhere. Therefore, you cannot assume the flow is irrotational. But for high Reynolds number flow, if you're away from boundary, then you can think the flow is irrotational. Okay, any question? Or did I make you confused, as usual? So important message is, thickness of boundary layer depends on Reynolds number, and the thickness of boundary layer decreases as Reynolds number increases. And inside of boundary layer, vorticity is generated because no slip boundary condition. Away from the boundary, you can assume flow is irrotational. That makes your life much easier. Okay. I'll talk a little bit more about two-dimensional flow. So in reality, there is no two-dimensional flow. Everything is three-dimensional, no matter what you do. Okay. But if the variation in one direction is very, very small, or the flow doesn't depend much on the one of the three coordinates, then we can say approximately the flow is two-dimensional. In this case, for example, flow in x and y, and then we have u and v. Those are the two velocity components. So velocity vector for two-dimensional flow is this. And then this velocity vector has to satisfy continuity equation, which is most important, the equation for us because it's conservation of mass. You cannot lose, mass. So if velocity vector doesn't satisfy this equation, then you are losing mass and volume, which is not allowed. So this has to be true all the time. Now, you have two variables, and you might wonder, is there any way? You might wonder if there is any way to reduce the number of unknowns to 1 from 2. There is a way to do by introducing a function. So let's say u is some function, y derivative of some function psi. Okay. And v, if I write this way, I don't know what psi is now, but if I can write u as this, v as this, then what happens? du dx plus dv dy is equal to d dx d psi dy plus d dy minus d psi dx, right? I just substitute the definition of u and definition of v here. And then you can see this is nothing but second derivative of psi in x and y. So this guy is identically 0. So this particular representation satisfies continuity equation all the time, no matter what psi is. Because, if I substitute these definitions into continuity equation, the left-hand side of continuity equation, that gives, 0 all the time, no matter what psi is. So this is a very convenient representation for incompressible fluid. For an incompressible. So for two-dimensional flow, we can introduce some function psi, and then u velocity is defined by d psi dy, and v as a minus d psi dx. Then this equation is automatically satisfied, so you don't have to worry about conservation of mass. Okay. The question is, what is psi? That's what we have to find out. Okay? And so to give what the psi is, let me give you the the physical meaning of psi. Psi is called stream function. Okay, which depends on, of course, function of x, y, and t. This is only for two-dimensional flow. at a fixed time, psi xyt equal to constant. So this is a fixed, this is constant. And then this will give you a curve, right? So this equation, when I say psi is some constant, that 0, for example, then t is fixed. And then this gives you the relation between x and y. And that is nothing but a representation of curve. So, for example, x minus y is y equal to x, which is a linear curve. So this gives a curve like this. So this is the curve that I can get when I fix time and this constant. This line is called the streamline. So streamline is a line of psi equal to constant. This is a line with and then what we can see is the following. So along this curve, psi is constant. So deep psi, the variation of psi along the curve, so along this curve, psi doesn't change, right? Because here I fix it the same, I have the same psi here, 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 everywhere. So if I move a little bit, then psi would not change. And from chain law, this means deep psi dx plus deep psi dy dy. Okay, so this guy has to be 0 because along the this curve, the stream function doesn't change, and meaning that this is deep psi dx is minus v dx, and the deep psi dy is u dy. And you can think this as minus vu, product between two vector. Okay. So this is the dx, and this is dy. So from here, what we can see is if the velocity vector, so this has to be 0 because nothing changes along the stream line, and therefore we have this. This means u and v is parallel to dx and dy. The reason is minus v u and v is given, will be minus uv plus uv is equal to 0. Okay? So this means dx dy has to be parallel to u and v, meaning that this is a velocity vector as well. Okay? So finally, streamline is a line of psi equal to constant, and also a line which the velocity vector is tangent to. So velocity vector always tangent to the streamline. So this is a velocity vector u. You cannot have velocity vector like that if this is a streamline. the velocity vector has to be always, the tangent to the streamline. So this is the physical meaning of this stream function. So stream function equal to constant gives you a streamline. And once you know the streamline, then you can draw the velocity vector or flow direction. And then u and v can be represented by this way. And by doing so, we don't have to worry about the conservation of mass. So probably you saw many pictures or drawings like this, right? So if you have a circular cylinder, you probably see something like this. And then this is really streamlined, and the velocity vector is always tangent to the streamline. Okay? So this is what you see here is a streamline. And once you have a streamline, you know the velocity vector is always tangent to the streamline. By just looking at the streamlines, I don't know the magnitude of velocity, but I do know the direction of velocity field. Okay. So once again, this is a mathematical definition of the stream function psi. And I haven't talked about how we get the stream function psi yet. And when next time I'll talk about equation of vorticity, then at that time I can show you how you get the stream function from Navier-Stokes equations. Okay. Okay. Any question? All right. So we're not going to have any classes next week, as I said at the beginning, and I'll see you in more than a week later. And also, I won't be available from Wednesday. So if you have any question about the homework, you can ask the TA Sungjin, Yun Sungjin, or you can ask Monday. Tuesday is a holiday, so Monday you can come to my office, or you can come to on March 7th as well. But before that, you can stop by Sungjin's office, which is first floor. So you can get some help from him. Okay. All right. Then see you later.